Welcome to the first talk of today's workshop. This is the last day, and today we have Professor Shoemaker. He is going to tell us about extremal transitions in Gromov Witten theory. Thank you.
Okay. Thanks for the introduction and for the invitation. Yeah, so I'm going to be talking about transitions in Gromov Witten theory. The plan of the talk is I'll introduce kind of the basic objects of comparison, which are quantum D-modules, which are defined via Gromov Witten invariants. Talk about some known results about Gromov Witten theory on different spaces, and then get into transitions from there. So the setting is we have a smooth projective variety. And these conditions can be relaxed, so it doesn't always have to be projective. You can replace variety with DM stat. And just to introduce the notation, so just to note Gromov Witten invariance as follows. So given a choice of cohomology classes in X, and coefficients are always complex here, and then if you're looking at an orbifold or a stack, you replace this with Chen-Rowan cohomology. We can define the genus G degree D Gromov Witten invariant with these insertions. Which is roughly counting numbers of marked curves such that the marked points land on these classes. And a common theme in this story is we want to look at generating functions of these. So I'm going to set up the notation for that. So first, let's choose a basis. The cohomology, and just a formal point in cohomology then can be written like this, where the TIs are, we're thinking of these right now as just formal parameters. And then the generating function that I want to look at is going to be in Genus-zero. So the whole story today is in Genus-zero. And it's going to basically be all Genus-zero Gromov Witten invariants where the first n insertions are these ones, and then I can have arbitrarily many other general insertions. So this looks like summing over the degree. So I've chosen some basis for H2. And then I've got Novikov parameters for each of these degrees. The first n insertions are the alphas, and then I add k more insertions. It's the degree D genus-zero invariant there. Okay, and with this we can define the large quantum product. As follows, so the quantum product of alpha with beta is defined by how it pairs with a third class gamma. So this is the Poincare pairing on the left side here, and this is just defined to be the double bracket with these three insertions. Okay. And we can soup this up a little more to define a connection going to be on a trivial vector bundle whose fibers are the cohomology of X. And the base is just going to be a formal neighborhood of 0 with these TI parameters and then also the Novikov variables. And then there's this third variable Z. So I'll call this. And the connection's defined via the quantum product. So it's defined like that. There's also a pairing. And the connection is flat with respect to this pairing. So we've got these Z variables now, so the pairing is defined as follows. Just defined via the Poincare pairing. So given two sections of this vector bundle. Put a minus C in the first limit. And this data together is what I'm going to call the quantum D module. It's this trivial vector bundle with the flat connection of the pairing. So I'll just denote it QDM X and this data. So, I mean, I'm not telling the whole story here. As many of you know, there's some redundancy with these Novikov variables due to the divisor equation. There's also a way to differentiate in the Z direction, which is coming from the homogeneity properties of Gromov-Witten invariance. But just to get an idea of the results, this is what the object that we're going to talk about today. So an important question in studying Gromov-Witten theory is how do Gromov-Witten invariants of different spaces relate? The first fact I'm going to say is by construction, really. And this is just deformation invariance. So if I have two spaces, related by deformation, then the Gromov-Witten invariants are the same. And so, of course, then their quantum D modules are the same, right? So this is not super interesting. I can match up these insertions, by the way, because the cohomology of Z1 and Z2 is isomorphic. But the reason these invariants are equal, again, from a mathematical perspective, is we're constructing them so that they will be. But the next one's a lot less obvious. So this is crepant resolution, crepant transformation picture. And so one form of the statement is the following. You have k-equivalent varieties. So this means that they're birational. And there's some space living above them. birational to both, such that if you pull back the canonical on each side, they're isomorphic. Okay. And this is going to imply, again, that their cohomologies are isomorphic, and the more interesting fact that is not known in full generality, but is now known in a lot of cases, is that the quantum D modules are also related. So, the example to have in mind for this picture is the Atiyah plot. One example. So, in terms of the toric picture, this is the fan for OP1 and -1. Two copies of O minus 1 OP1. And you can do a birational transformation to get this fan, which is also isomorphic to 2 copies of O minus 1 on P1, but in a different way. So the fiber directions here correspond to the compact directions here. And the relationship between the quantum D modules is complicated, and the reason for that is the following. So the cohomology of these two is isomorphic, but one way to do this is to pull back and then push forward. But that isomorphism is not preserving effective classes. So, for instance, in this case, let me just call C1 the copy of P1 inside of here, and C2 the copy of P1 inside of here. If I look at what this Fourier-Mukai transform does to the curve, this curve class, get the negative of C2. And that, that's got implications in terms of how these could be related, because the Novikov variables then aren't matching up in any obvious way. So the Novikov variable, the Q, corresponding to degree on this side, QZ1, which I can think of as Q to the 1 times the class of C1, this is going to, if I want these to match up in any reasonable way, it's going to have to correspond to Novikov variable on the Z2 side with a minus sign. Okay, and so what this tells you is that there's no straightforward way to match these up, because the power series on one side is going to correspond to something with negative coefficients on the other. And so what this squiggly means is that they're actually going to be related by analytic continuation. So let me just say some names that have worked on this. And it's a long story, so I can't say everybody, but there have been various versions of this result and various levels of generality, but some people that formulated statements along these lines are Li Ruan, Brian Graeber, who noticed the importance of analytic continuation here. Leland Wang, and others, but the theorem that I'm going to really use today.
I mean, in which parameter do you analytically contain? In the scalar parameter? Or?
I'm just thinking in the Novikov variable.
In the Novikov, you do analytic continuation.
Yeah.
And so what are the principles of this analytic continuation? You have somewhere an analytic function, and then...
So I'm about to state a precise result. Maybe you can ask if there's still a question. Yeah. Yeah, I mean, I know this is vague. This is just kind of an indication that something complicated has to happen. But the theorem that I'm going to use, so I'll state it a little more precisely, is the following. So this is for toric varieties. So if Z1 and Z2 are toric, so that example in particular. Related by variation of GIT, the following is true. There exists, after a mu transformation, a global object, so a global D-module on a formal thickening of P1 such that if I expand near zero, what I get is pullback via the Mir transformation of the quantum D module of C1 and expansion near infinity is the other. So what I mean by this formal thickening is there's a particular direction I can go in this set of parameters, which is analytic, and I'm formal in all the other directions, and then you have this statement. But this is all actually up to a Mir transformation, so we're working on some I guess some formal neighborhood of a P1 in the secondary pan for the toric GIT data. So that's the crepant transformation conjecture. And
Is P1 the Z in the
what was the variable?
The coordinates of P1.
Not Z. So I mean, morally it's the cube parameter, but actually there's a Mir transformation, so it's a little more complicated than that. If you don't like I functions and stuff, and would prefer a cleaner statement, I think Leland Wang had a lot of results where they're actually working with the Novikov variables. So,
From what thinking of P1 is a scheme with reduced scheme. The formal thinking.
Yeah, so what I'm saying is, you remember previously I had all those T variables, right?
Right.
So one of those you compactify, so you have a P1, but the others, sorry, one of them is analytic.
Ah, I see.
It's actually analytic and then formal and all the other parameters. Yeah.
But, so this D model, can you think about it as a differential equation on this analytic parameter? Or?
Yeah, so you get collection of differential
Right.
equations.
And that is basically like doing analytically continuing solution of differential equation. Is that
Yeah,
what
yeah,
happens?
yeah. So I mean, this is the global D module is coming from the GKZ system. Yeah, exactly.
How come you can analytically continue in one variable but not the rest? Like you have to already know that you have a VGIT transformation on the other side to be able to analytically continue?
You have to already know what?
You already need to know that you have a VGIT transformation on the other side to be able to analytically continue in a certain direction? Like
You don't need to know it. I mean, so again, they're using the GKZ system, and they're checking that in one direction, it's got a finite radius of convergence, and you can analytically continue. But I don't really know because, in the setup they always do, so maybe that is necessary. I'm not sure about that. Okay, so let me talk about transitions now, and the motivation for them is coming from the previous two correspondences. So let's say we start with a singular variety. Then there's two natural ways to recover something smooth from it. The first is deform, and view this as a degeneration of a smooth variety. And the second is to resolve singularities. So let's say we can deform Z bar to get something called Z, and if there exists a crepant resolution of singularities, we'll call that Z twiddle, and then the passage, or just the relationship between Z and Z twiddle is called a transition. So the picture is I have some Z which degenerates to something singular, Z bar. And then there's a birational map here. Which is crepant. So this is the picture for a transition. And based on the previous two results, it's kind of reasonable to hope that the Gromov-Witten theories of these two should be related. Why? Because if the Gromov-Witten theory of Z bar made sense, then these two should be the same, and this is a crepant transformation, so these two should be related. So it's something you might hope, but immediately you see that it's not that simple. Because, for instance, the cohomology of these are not isomorphic. And so it's already going to be necessarily more complicated than, for instance, the crepant transformation conjecture. Let me just give you a local example of this to have in mind. So the singular one is the toric variety defined by this fan. And this looks like xy minus w equals 0. So I can easily deform this by changing that parameter. So I can let Z be this, for instance, and I can resolve singularities to get toric variety we saw before. By just splitting this cone into two simplicial cones. Okay, so why might one want to study this question about the Gromov-Witten theory of these two objects, besides the fact that it seems reasonable that there might be something to say? Well, the motivation to study them comes from mirror symmetry as well as Reed's fantasy. So, the idea is, at least historically, although we've seen talks this week that say more, but historically, mirror symmetry is looking at the Gromov-Witten theory of Calabi threefolds, and if you want to study mirror symmetry, it's complicated because there's a lot of Calabi threefolds, right? And in fact, the moduli space of these is very large and it's disconnected. But Reed's fantasy says the following, that if you look at the moduli space of smooth Calabi threefolds and compactify by allowing singular things, so like Z twiddle and Z are going to be on different components of the moduli space, different connected components. But if I declare that these two should be equivalent, because they're related by a crepant resolution, so I declare those to be equivalent, then maybe the moduli space is connected under that equivalence relation. So, more precisely, the fantasy, the hope, is that maybe any two smooth Calabi threefolds are related by these transitions.
But now, which transition you mean exactly? This cannot be just this irrational stuff, right?
So the I guess Reed's fantasy is by extremal transitions. Yeah. And so I'm being loose about whether or not I'm saying extremal or not. So okay, maybe they're related by extremal transitions, and then Morrison has a result that says if you apply an extremal transition to some Calabi threefold, then, well, specifically I guess he was talking about conifold transitions, then the mirror also changes by a conifold transition. So if you can understand how the Gromov, how the A model changes under some type of transition, and the mirror is also related by a transition, you might be able to prove mirror symmetry for all smooth Calabi threefolds, more than just the cases where we already know what the mirrors are. If I change M by a conifold transition, then the mirror also changes. By a conifold transition. And so, if you extend this to extremal transitions, and if this is true, then you can prove mirror symmetry for all Calabi threefolds. So that's a motivation for it. So previous work on this question. This same paper I mentioned before, Lee and Rowan, thought about conifold transitions. And they showed that, so in this setting, not just the local model, but any conifold transition, Gromov-Witten theory of Z twiddle covers the Gromov-Witten theory of Z. So it's not bidirectional anymore, right? Li, Lin, and Wang tried to make a statement that was symmetric in Z and Z twiddle, and so what they were able to show was that if you look at the A model and the B model of Z twiddle, you can recover the A model and the B model of Z, and vice versa. So if you look at both the A side and the B side, you can recover either from the other. But again, these are both for conifold transitions. And then going beyond conifolds, Iritani and Zhao, 16, and then Rongxiao Mi. Showed statements, again in the flavor of the crepant transformation conjecture, in the sense that they were statements about the quantum D-modules. And this was for specific examples, but that went beyond the conifold case. And Rongxiao made a conjecture that says sort of what maybe we can hope to expect for more general extremal transitions. And I'm going to paraphrase slightly his actual conjecture so that it's more in line with things I've said previously. So if these are related by extremal transition, then the following should be true. There exists, again, a global D module on a formal thickening of P1. Such that if I expand near zero, I recover the quantum D module of Z twiddle. And then around infinity, something different happens. So I look at the monodromy invariant part around infinity. And then I restrict that to infinity. And this D module contains quantum D module of Z as a submodule. Okay, so it looks a lot like the crepant transformation conjecture I stated before, but it's no longer equivalent if you change z and z twiddle. Basically, it's a very precise way of stating that the genus-zero Gromov Witten theory of z twiddle can recover the genus-zero Gromov Witten theory of z.
Can you add the variation of post structure to make it equal extent? I mean, meaning A plus B.
A plus B?
Yeah.
I mean, well, I haven't looked into it, but my guess would be that there is, yeah, probably yes, if you phrase it correctly. So the theorem by Rongxiao and myself is that the conjecture holds for a certain class of transitions. So transitions between hypersurfaces in toric varieties where the transition arises via a blow-up of the ambient toric variety. Okay. So the upshots here is it's pretty general in the sense that it's not just specific examples, it's a large class of transitions. In particular, we're not just looking at threefolds, and we're not just looking at Calabi yaos. And we're not just looking at conifold transitions as well. And the thing that I like the most is it really gives a geometric explanation for a lot of the things going on in this conjecture. So we can see immediately why the analytic continuation is coming into play. And why we have to do this restriction. And then one final thing is these quantum D modules have extra structure of an integral lattice, which is Irritani's integral structure, and it matches those as well.
I think Li-Lin Wang is a big theory, right? But Irritani and Xiao is a small theory, right?
Is small what?
Small quantum moduli.
I don't know. Sorry.
So I just checked. That's what I said.
Okay. Okay.
So this is a big quantum moduli.
This is big. That's right. That's right. So it really uses Coates-Irritani Jom, which is a statement about the big quantum D module. But there's a mere transformation in there, which I didn't write. Okay. So let me give you kind of the setup in which our results hold. And this is, I'm just going to restrict to the Calabi Yao case because it makes the exposition a little more simple. Okay, so these are going to be hypersurfaces and toric varieties. So let's start with a toric variety. So the toric variety is coming from some fan sigma, and X sigma is going to be the corresponding stacky toric DM stack. And what this reflexive condition gives me is that if I take a general section of the anti-canonical, its zero locus is going to be a smooth Calabi. So that's Z. And then I'm going to do a blow up. So I choose a cone inside of sigma. And let's say it's spanned by the rays. The primitive ray generator is rho 1 through ray k. I'm going to let it be inside of x be the zero locus of the corresponding homogeneous coordinates. X is x sigma. And I'm going to add a new ray, which is corresponding to a blow-up. Add a new ray to the span. And the ray is going to be, its generator is going to be the sum of these rho x. So I'm adding a new ray inside of this cone sigma, and then I can do a subdivision to get a new fan. Which I'll call sigma twiddle. So that's going to be the ambient toric variety for Z twiddle. But first I want to generate my section. So I'm going to let S prime be a section of the anticanonical of X. Which vanishes on V to order k minus 1. And if I do that, so then my Z bar is going to be the vanishing locus of S prime, which might attain singularities along B. But the way I've set this up, S prime is also going to define a section of the anticanonical bundle of X twiddle. And then under some conditions on the fan, so if sigma twiddle is also reflexive, then inside X twiddle, the hypersurface defined by this section is also going to be a smooth Calabi. And so Z and Z twiddle then are connected by this extremal transition. And this is the context, at least for Calabi-Yaos, in which the theorem holds. Okay, so let me talk about the proof of the theorem. The key new ingredient here is yet another comparison result about the Gromov-Witten theory of different spaces. And that result is quantum state duality. which mathematically was first proven by Coates-Giventhal, and then reformulated in a way which is useful for us because it involves the quantum D module, later by Iritani, Mann, and Mignon. And what it says is the following. So, given X smooth projective, let's say I have a vector bundle on X with a regular section, and I look at Z, a smooth hypersurface defined by the section. Okay, so I can look at the Gromov-Witten theory of Z. On the other hand, you can consider the Gromov-Witten theory of the dual of this vector bundle E. So Z is the quintic. This is O of minus 5 on P4. And the statement says that these are, the Gromov-Witten theory of these two is related. So first, I'm not able to look at the full quantum D module of the hypersurface, just because it's hard to calculate the primitive Gromov-Witten invariance for the hypersurface. So I restrict to the cohomology coming from X. So, sorry, I missed a line. So I have a pullback map from the cohomology of X, the cohomology of Z. I define the ambient cohomology of Z through the image. Okay. And it turns out that the quantum D module restricts to this cohomology under some relatively mild assumptions, and so I can define an ambient quantum D module. And also, for a non-compact space, again with some mild assumptions, I want to look at the compactly supported cohomology of Y. So let's say I'm looking at Durand cohomology, I can forget that it was compactly supported and I get a map to the usual cohomology. I'm going to define the narrow cohomology of Y to be the image under this forgetful map phi. And again, the quantum D module behaves well with respect to this subspace of the cohomology of Y, and I can define the narrow quantum D module. And so the theorem says that there's an isomorphism after some change of variables between the ambient quantum D module of Z and the narrow quantum D module. So in our case, we have two hypersurfaces, Z and Z twiddle, living inside two toric varieties. And this result says that rather than looking at the quantum D modules of the hypersurfaces directly, I can look at the total space of the canonical bundles on those toric varieties. So D is the total space of X sigma. Let's let T twiddle the total space of the canonical on sigma twiddle. Then the ambient quantum D module of Z or Z twiddle is isomorphic to the narrow quantum D module of T or T twiddle respectively. So that's the first reduction. What's nice is that these are toric varieties, so we can use what's known about Gromov-Witten theory of toric varieties, which is quite a lot, to our advantage. So let me give a sketch of the proof then. Be a specific example. So let's let Z be the quintet. The Fermat quintet plus Z inside P4. So that's my X. So I can degenerate this polynomial or deform it. So the way I do this is I let F and G be general degree 4 polynomials, and I define Z bar as follows: be X naught times F plus X1 times G. And this one's going to be singular. At 16 points, defined by the vanishing of these 4 polynomials. Okay, so this is kind of a classic example. And then if I blow up at the P2 defined by x0 and x1 equals 0, gives me a new ambient space x twiddle, and then the proper transform of this is going to be my Z twiddle. So that's the example. And what I want to do is I want to draw the bands for the toric varieties of the canonical bundles on X and X twiddle. So first I'll draw the bands for X and X twiddle. So these are the rays corresponding to the first 2 homogeneous coordinates, and then this ray is going to secretly denote the other 3. So this is a picture. And then the blow-up, I'm adding a ray, which is the sum of these 2 rays. Those are the ambient toric varieties, and then I want to look at the toric varieties corresponding to their canonical bundles. Okay, and the way given a toric variety, the way you construct or given a fan, the way you get the fan for the canonical is you raise these ray generators to height 1, add a new vertical ray, and extend those cones. So we'll start a new page here. So the fan for T looks like that. So this is like the height 1 slice. There's 4 primitive ray generators there. And then T twiddle, I raise this to height 1. So it looks like that. Okay. And the observation here is that there's an intermediate space which kind of interpolates between T and T twiddle, and it looks as follows. instead of splitting this cone this way, I do that. Okay. And this is really the key idea of the paper. I want to emphasize that this also appeared in David's talk, a similar concept, and it's been used by him and Tyler Kelly in a lot of their papers on derived equivalences for different mirrors. But the idea is the following: these two are related by a flop, right? And they're toric, so we can apply the crepant transformation conjecture, which I had written here earlier by Coates-Irotani Zhang, to relate their quantum D-modules. They're related by analytic continuation. And then we need to figure out the connection between T-bar and T. Well, T-bar is a partial compactification of T. And if you investigate it carefully, what you see is that there's one, as you go from T to T bar, there's one new curve class. Which is connecting this locus to this new locus here. So you get a new curve class, you get a new Novikov variable as you go from T to T bar. And morally, this is exactly the variable that you want to analytic continue in to get from T-bar to T-twiddle. However, if I look at the quantum D-module for T-bar, and I set that parameter equal to 0, it contains the Gromov-Witten theory of T inside of here, because if I'm not allowing these curve classes, stable maps into T-bar have to land entirely here or entirely here. And so the D-module is going to split once I set this equal to 0, and I'm going to see the D-module of T living inside there, really directly. So, and then you apply quantum state duality directly. We've got this connection between T and T-twiddle exactly the way the conjecture stated. Those are isomorphic to the quantum D-modules of Z and Z-twiddle, and that's the proof. Guess I wanted to say just a couple more things, just notes to end on. Some upshots of this is that all of these operations are compatible with Irotani's integral structure, so I think something new that we get from this method is that these, the Gromov-Witten theory of transitions is compatible with the integral structure on the D-modules. You might wonder, does this generalize beyond toric varieties? Because of course, the original motivation for looking at extremal transitions was exactly to get out of the land of toric complete intersections, toric hypersurfaces. And the answer is that I think optimistically there's a good hope of that, because the quantum state duality result has nothing to do with toric varieties. So the main place we're using it is the crepant transformation conjecture, which already, for instance, Li, Lin, and Wang have a lot of results that go to a very general setting beyond toric varieties. Yeah, I think I'll stop there. Thank you.
Any questions?
Rick, when you said the quantum D module sits as a submodule, does it just split at the end then? Or is
Yeah.
Okay. So does it look almost like on the B side, the semi-orthogonal decomposition? It's exactly the analog of that.
I would guess yeah, but once you set that parameter to 0, yeah. I think that's right. That's my best guess. Yeah.
Do you have some understanding of why, even in Rongxiao's original conjecture all these curves were P1s as opposed to like higher genus curves potentially on which you have to analytically continue?
Oh, when you analytically continue? In this setting, the P1 is coming from the secondary fan, and so you're taking the secondary fan, and you're just looking at a curve connecting two of these zero loci, and so that's going to be a P1. I think, Rongxiao can correct me if I'm wrong, but I think his examples fall under this general setup, and so I think one answer to your question could be that it's coming from something toric. Yeah.
Okay. Is the expectation that it's still P1 even in more general cases of transitions or crepant resolutions?
Yeah, that's expected to be the case for general thing, very general thing.
What?
Can you think like in the Cater cone, you're really closing the Cater cone. And then torically, that is the P1. If they're toric, it's
Yeah, if I'm
it's
toric,
bad.
right, yeah.
But in the Cater cone perspective, you're continuing on the Cater cone. That typically more drives the fan.
So can you say more about the integral structure? You said compatible means what? So is it about the flop method?
In the flop part of the proof?
Yeah. So I mean the integral structure. You said that it's compatible with this process.
Yeah. So to connect these two, that's part of Kosirotani Zhang's result is they show that they find another toric variety which lives over these, and they show that the Fourier-Mukai transform is exactly compatible with the analytic continuation. And so, if you take, are you familiar with Irutani's integral structure?
Yeah. At least I have seen it.
Yeah. So the input is a class in K theory, and the output is a flat section of the D module, right? And the Fourier-Mukai transform, taking K theory of T bar to K theory of T twiddle, exactly matches analytically continuing the corresponding flat section. And so that's that part. This one's pretty automatic, and then the quantum Serre duality result as well, I showed that is compatible with the integral transform.
So for the identification of the quantity module, is there any conjecture relating the Pfaffian-Grassmannian setting?
Oh, probably. I don't really know that story very well, to be honest with you. Probably other people in the audience know better than I do. Yeah?
Because you realize two toric variety, is this possible? I can write two Genus model for this two model.
Yeah, so I know we talked about this yesterday. I'd be happy to show you exactly. And it's in my notes, but I ran out of time. So in the background of the ideas behind this proof is gauge linear sigma models. So the hypersurface Gromov Witten theory exactly corresponds to the enumerative invariance of the gauge linear sigma models of the total space of the canonical bundle with the corresponding potentials. And so both of these have GLSMs, and T bar does as well. It's the same potential on T twiddle, you're just doing a different GIT quotient, right? And so the expectation is certainly that the gauge linear sigma model invariance of these two should be related in the same way as the crepant transformation conjecture, and these two should correspond to. I mean, it's exactly the same as this picture, but gauge linear sigma models. But I think if one wants to prove higher genus types of results with transitions, that's the way to look, right? Because quantum Serre duality fails after genus zero. And so to do higher genus stuff, you're going to need to use the gauge linear sigma model. Yeah, so not the higher genus part, but looking at these GLSMs is a work in progress right now, but you can kind of guess what the answer should be. Yeah.
So far, it's only really the web is a high genus field. The other high genus is
Actually, so I'm going to say, so Coates, Iritani, Sang, and I can't remember exactly which authors, but some possibly non-proper subset of Coates, Corti, Iritani, Sang have a higher genus, pretty much the full story for toric varieties for the crepant transformation conjecture. There's certainly others that I'm not remembering right now.
Yeah, let's thank speaker again. And there is an announcement for the reimbursement.